In this video, we will explain a very significant part of the communication systems. This is the channel. The channel is everything that happens between the transmitter and the receiver. There are two types of channel. The guided ones that imply a wire between the transmitter and the receiver. So good examples here are the optic fibers and every wire that you can think about. The second type of channels is the non-guided one, so the radio channels. In this course, we will focus only on the radio channels. Of course, it's many times harder to deal with radio channels than with guided ones. Let's define channel. A channel is everything that happens between the transmitter and the receiver. This is between the antenna of the transmitter and the antenna of the receiver. Sometimes we model into the channel some things that in fact happen in the receiver, but this definition, I think it's very helpful for us. The next question is, what happens between the transmitter and the receiver? And the answer is that it happens a lot of things. The signal gets attenuated, it loses a lot of power. The signal gets noisy, the signal gets interfered, and also the signal gets distorted. What's the attenuation? The attenuation is the loss of power of the signal between the transmitter and the receiver. It depends on many parameters. The first one is the environment. This attenuation won't be the same on an indoor environment like your house than outdoors, for example, or into a railway tunnel. The signal will behave into a different way, so the attenuation will be very different. The second parameter is the frequency. This is not very intuitive, but later on we will go into more details on it. The third parameter is the distance between the transmitter and the receiver. This is a very intuitive approach, because the more separated the transmitter and the receiver are, the more attenuated the signal will take. This seems logical. In the middle of the slide, you can find an expression that relates the transmitted power and the received power. This formula, in this example, is only for free space communications. This is the so-called freeze formula, to honor the Danish engineer who discovered this relationship. In a more general way, you will need to include the gains of the antennas. Don't panic if you don't understand why we add these gains to the previous expression. In later videos, we will talk about antennas and you will learn about the gain of them. Another parameter that affects the signal is the noise. As you will probably know, the noise is an undesirable feature of the signal, and we model it as a random process. The cause of this noise is the movement of charged particles. This definition may not help you, but it's good to understand that noise is everywhere. It's present on every frequency. It's everywhere. And a very important parameter about the most common noise that we will need to deal with is that it's related to temperature. The hotter your system is, the hotter your wire is, the hotter everything is, the more noisy it is. This thermal noise, we model it in the way that you have in the picture. It's a flat noise. and we call it white noise. But it's important to remark that not every noise is white, so not every noise is flat in the spectrum. Our thermal noise is uniformly distributed along the spectrum. This means that its power, or to be more precise, the power density, so the power divided by the bandwidth, it's constant along all the frequencies. This is true up to 1 terahertz, but that's enough for the purpose of this course. So you can suppose that the spectral density of the noise is flat on every frequency you work in. A very important point here is that the power of the noise is proportional to both the spectral density, the NO parameter that you have there, and also the bandwidth. The more bandwidth that you have, the more noise that gets into your signal. So it's a good moment now to understand that you will need to filter that noise, to reduce the bandwidth in order to remove the noise. A very important parameter in communications, it's the signal-to-noise ratio. This ratio relates the power of the signal with the power of the noise. The desired power, the power of the signal, what we want to transmit, and also the power of the noise, which is something that we don't want to have. Of course, this means that we want the SNR to be as high as possible. Which ways do we have to calculate or to deal with the noise? We can use a spectrum analyzer. Now that we know about noise and also about logarithmic units, and we understand what a spectrum is, we can learn about the spectrum analyzer. A spectrum analyzer is a device that plots on a given spectrum the signal power versus frequency. This is a good example of this. It is a capture of a measurement that I took long ago. Here you can see it's a certain band around 5 gigahertz, and you can see some power and also some noise. How does this spectrum analyzer work? It has a narrowband filter that sweeps through the entire range of frequencies. On each band, on each narrow band, it calculates the power on this frequency and plots it on the screen. So these measurements depends on the width that you are measuring. It has some parameters that you need to know: the central frequency, the span, which is the total bandwidth that will be depicted in the screen, the reference level, which is the highest power that you will see in the screen, the vertical step, this is the scale, the vertical scale, how much dBs you have per square, also the resolution bandwidth, which is the step which you are measuring the power, and also the input attenuation, which helps us to place the signal in the screen. Here you have a good example of a modulated signal. You can see the signal circled in blue, and also you can see on the left and in the right the noise. It's a noise floor. If you can see the screen, you can see the noise power and also the signal power. Distortion is something that all the communication electronics do to the signal. For example, look at the blue signal on the left. This signal needs to be amplified, and the result of that amplification process is the red signal on the left. There is no distortion, only amplification. There is only gain. There is only a parameter, the gain between the blue signal and the red signal on the left. But let's look at the right. You have a blue signal and you amplify this signal, but on the top, the peak of the signal, it's a little bit trimmed. So this means a distortion. Another way that you can see the distortion is on the frequency domain. For example, let's look at the picture on the top. You introduce one tone. A tone is a signal which only has one frequency. Its spectrum is very, very narrow. And you want to amplify that signal. So you expect only one signal in the same frequency. But for your surprise, you find out that there are a lot of frequency components. These components are harmonics and mean distortion. These distortions causes a decrease in the gain of the amplifier. On the bottom you have another example with two tones, and the result it's a little bit more complicated, but the philosophy is the same. There are many other effects that channels and receivers and everything between the transmitted signal and the received signal can do on the signals, but it's enough for the moment. We need to understand the attenuation, the noise, and the signal-to-noise ratio. There are three very important parameters, and the spectrum analyzer is the simplest tool to deal with them. Thanks for your attention.